Hi students, this is Sai Abhinav. So today I am going to give a lecture on energy theorems. So this is the unit number 4 comes in structural analysis. So first of all, what is the basic definition in energy theorems? So we'll discuss that one. So first of all, what is meant by energy and strain energy? So what is meant by energy here means so basic definition is energy means the capacity to do work is known as energy. So everybody know about that one. So how much of how much of capacity to do that particular work is known as energy. As the same thing when it comes to the our structural analysis. So how much of internal energy is there when an elastic member is subjected to an external load, how much of energy in internally is known as a strain energy. Okay, so here it is one I mentioned one definition when an elastic member is deformed under the action of external loading. So the member is said to have some stored energy. That stored energy is known as strain energy. So it directly is there. So when a member, elastic member is subjected to an external load, it stores some energy is known as strained energy. So next, one of the basic important note here, strain energy stored. How much of strain energy stored inside or internally? It must be is equals to how much of work done due to the external load. So it is the equality or equilibrium condition. The strain energy is the internal energy. It must be is equals to how much of work done happening on particular due to the external loading. That is the basic equilibrium condition. So how much of internal energy is there? How much of work done is happening on outside? The next one, then move to the strain energy stored due to the axial loading. So this is the first derivation we'll discussing. Okay, so how much of strain energy is storing inside the member due to the axial loading. Okay, next one. So strain energy due to axial loading. So first of all, I am considering an elastic member and it is subjected to a load, axial load W, and it is having length L and area capital A and W, sorry, load be the W. So after adding the load or after subjected to an axial load, the member is automatically deformed. So that is change in dimension. So I am mentioning or I am treating as delta. So, so what is the work done is happening. So work done means here it is an external source to get a deformation. Okay, so that is the external. So external means here work done. What is internal? Internal means here strain energy. How much of energy is stored? So by the application of external. So that is the difference. We have to observe that one. Okay. So work done. How to calculate this work done means here it is two ways. One is work done by the load on the member. It must be is equals to product of average of load and displacement. So work done is equals to what is the product of average of load and displacement. So what is the load I mentioned here? W. So W into what is the displacement here? Delta. So that is product. But here it is average load and displacement. So that so work done is equals to half into W into delta. And another formula we can get the work done. So from the x and y axis, so load is acting in x axis. You can take the load in x axis and displacement in y axis. So area of this triangle. So if the load is acting and strain also you can get. So by area of this triangle, what is the area of the triangle? Half into base into height. So here half into load into deflection or displacement. So from that we can get the work done also. Next here it is external work done is equals to WE is equals to half into load into deflection. So what is the internal energy means here? Strain energy. So we call it as directly U. So now actually I have to tell about what is the indication of strain energy is U, capital U. Okay. So next one, I'm taking tension in the member is S. So for equilibrium condition, load W is equals to tension in the member. That is the equilibrium condition. So why? Because means here I'm acting axially member. So that axial means here it is some tension is acting. So the load is must be is equals to tension in the member. So here I am taking the tension. So the tensile stress. What is the stress formula? Load by area, force by area. So that I am taking stress is equals to tensile force by area. As the same thing, tensile strain is equals to stress by Young's modulus. Another formula is also there, that is change in dimension by original dimensions. From the Young's modulus, what is the formula? Stress by strain. When you separate strain from this formula, stress by Young's modulus, we already know about this stress, load by area, tensile force by area. From change in length by original length, when you separate the change in length, it must be is equal to strain into original length, and therefore when you substitute the strain S by A E into L, we can get. And finally already discuss about one note, the strain energy is equals to work done. Simply you can say internal energy is equals to external energy. External energy means here work done, internal energy means here strain energy. So therefore strain energy is equals to work done. So that half into load into displacement. So from the equilibrium condition, load is equals to tensile force. I am writing load is equals to tensile force. So we already defines change in length, delta is equals to S L by AE, and finally we got S square L by 2AE. So when you calculate for strain energy per unit volume, it must be is equals to S square L by 2AE. For unit volume is here length, breadth and height, but or another right, another one area into length. So area into length I'm writing. So it is I'm cancelling L and finally we got S square by 2A square into E. And what is the formula for stress? Here S by A is the stress formula. So here I'm writing S by A. In the means of S by A, I'm writing sigma square by 2E. So this is the formula for strain energy subjected to axial loading. So very important for derivation for 5 marks question also.